The Victorian lighthouse clockwork mechanism represents a century of continuous mechanical operation without a single failure in lens rotation. Between 1822 and the 1980s, these systems kept Fresnel lenses weighing up to 6 tons rotating with absolute precision through Atlantic gales and constant salt exposure. The engineering solution combined 3 elements: a mercury bath bearing that eliminated friction, a weight-driven governor maintaining constant speed, and a clockwork escapement ensuring rhythmic accuracy. Augustin-Jean Fresnel introduced his multi-panel lens design in 1822 at the Trough lighthouse in France. The lens concentrated light into a narrow beam visible 30 miles at sea, but rotating this assembly required overcoming significant mechanical challenges. Traditional bearings seized under the combined stress of weight and constant motion. The mercury flotation bearing, developed by François Soleil in 1825, provided the solution. A circular trough 14 inches deep held 300 pounds of liquid mercury. The lens assembly rested on a cast-iron float, displacing exactly its weight in mercury, creating a friction coefficient of 0.0001. The weight-driven mechanism operated like a grandfather clock, scaled to industrial dimensions. A steel cable wound around a drum supported cast-iron weights, totaling 800 to 1,200 pounds. Gravity pulled the weights downward through a shaft descending 60 to 90 feet into the lighthouse tower. The falling weight rotated the drum, which turned the lens assembly through a series of reduction gears. A typical first-order lighthouse lens completed 1 full rotation every 90 seconds. The gear train reduced the drum's rotational speed by a ratio of 240 to 1, converting the weight's rapid descent into the lens's slow, steady sweep. The clockwork escapement regulated the weight's descent with mechanical precision. A verge and foliate mechanism, refined from medieval clock designs, controlled the gear train's movement. 2 weighted arms oscillated on a vertical shaft, engaging and releasing gear teeth in measured intervals. This created the characteristic tick-tock rhythm that lighthouse keepers used to verify proper operation. The escapement maintained rotational accuracy within 2 seconds per hour, ensuring the light's characteristic flash pattern remained consistent for navigational identification. Trinity House installed the first mercury bath system at Start Point Lighthouse in Devon in 1836. The mechanism rotated a 6-ton first-order Fresnel lens without difficulty. By 1850, 47 British lighthouses operated mercury-bearing systems. The United States Lighthouse Board adopted the technology in 1858, beginning with Cape Hatteras. Within 2 decades, every American coastal lighthouse above 4th-order classification used mercury flotation bearings. The system's reliability eliminated the constant maintenance required by previous roller bearing designs, which needed replacement every 6 to 18 months. Daily operation required minimal intervention. The lighthouse keeper wound the mechanism every 3 to 4 hours, cranking the weights back to their starting position. This task took 6 to 8 minutes, using a hand crank connected to the main drum through a ratchet system. The keeper checked mercury levels monthly, adding 5 to 10 pounds to compensate for evaporation. Annual maintenance involved cleaning the mercury trough with chamois cloths and inspecting gear teeth for wear. Properly maintained systems operated 40 to 60 years before requiring major component replacement. The system faced its first serious challenge during World War I, when lighthouse crews were reduced and maintenance schedules disrupted. The Bishop Rock Lighthouse off Cornwall operated for 7 months without adjustment in 1917, maintaining its 2-second flash pattern throughout. This demonstrated the mechanism's inherent stability. The clockwork compensated automatically for temperature variations through a bimetallic compensator that adjusted escapement timing. As ambient temperature changed, the compensator's brass and steel strips expanded at different rates, shifting the escapement's pivot point to maintain consistent rotation speed. Salt corrosion threatened exposed metal components, addressed this in 1888 by introducing sealed gear housings with grease-packed roller chains replacing open gearing. The mercury trough received a bronze liner resistant to salt-induced pitting. These modifications extended operational life from 30 years to 70 years without major overhaul. The Makapu Point Lighthouse in Hawaii, commissioned in 1909, operated its original mercury mechanism until 1987, a span of 78 years. The weight-driven system's independence from external power sources proved critical during storms. When electrical systems failed, the clockwork continued operating using only gravity. The Eddystone Lighthouse maintained operation through the Great Storm of 1953, which destroyed its electrical generator. The keeper simply continued winding the weights manually, ensuring the light's rotation never stopped. This redundancy saved numerous ships navigating by the lighthouse's characteristic pattern. Mercury's toxicity became the system's ultimate limitation. Environmental regulations in the 1970s restricted mercury use in new installations. The technology's replacement began not from mechanical failure, but from health and safety concerns. Between 1975 and 1995, most mercury bearings were replaced with ball bearing systems driven by electric motors. The conversion process carefully removed and disposed of mercury according to hazardous waste protocols. Some systems preserved their original clockwork as backup mechanisms, maintaining the weight-driven capability alongside electric motors. Today, 12 lighthouses worldwide maintain operational mercury-bearing systems as working historical demonstrations. The Point Reyes Lighthouse in California rotates its original 1870 mechanism daily for public viewing. The system requires no modern components. The same cast-iron gears, mercury bath, and weight-driven governor continue functioning after 154 years. Modern lighthouse systems use electric motors with computerized monitoring, but these require constant electrical supply and electronic maintenance. The Victorian clockwork needed only gravity and periodic winding. The lesson transcends lighthouse engineering. When designing for century-long operation, eliminate dependencies. The mercury bearing removed friction. The weight-driven system removed power requirements. The clockwork escapement removed electronic control. Each element solved one problem completely through mechanical simplicity. Modern systems distribute reliability across multiple components, creating multiple failure points. The Victorian approach concentrated reliability into friction-free motion, gravitational constancy, and mechanical rhythm. That combination outlasted electrical generators, computer controls, and maintenance budgets, proving that perfect mechanical solutions need no improvement.